All right, class. Welcome to the Mathcast for lesson 9.1.3, looking at three-dimensional solids, specifically prisms, whose bases are not rectangles. So this picks up with the ideas that we've been exploring in the first two lessons, where we're still in introductory level three-dimensional solids work. Specifically, we'll be looking at the volumes and surface areas for prisms and cylinders, um, expanding our knowledge to those figures that don't have rectangular bases. So throughout this lesson today, think about what you did in the past lesson and how you can apply the ideas of finding the area of one base and multiplying it by the height, and see if those continue to hold true as we change the shape of the base. Try to visualize the cylinder in different ways and try to unravel that shape into some more basic ones, and then really take a hard look at that Cavalieri's principle, which is introduced at the end. Throughout this lesson, just like with the last one, you'll have the answer key available if you need to check your work. Many of the questions, I think, with a little bit of thought, can lead you to the correct answers, but please don't hesitate to look at that. Going through the keywords that you'll need to really take a look at would be rectangular and triangular prisms, cylinders, Cavalieri's principle, and what it means to have an oblique cylinder or prism. So keep an eye on that vocabulary as you work throughout this lesson. At this time, go ahead and pause the lesson and then return for a lesson recap when you're done. But again, make sure you take your time because the focus of the learning is happening in the work you do, not in the brief recap at the end. All right, guys, good luck with the lesson. I'll see you when you're back. All right, welcome back. At this point, I hope you're joining me because you've thoroughly completed the lesson and you're ready to make sure you hit all the main ideas. So let's jump right into those. So when we talked about special prisms throughout this lesson, you worked with triangular prisms, which had triangles as the base, connected by rectangular sides. I also see a hexagonal prism in that same problem, which had hexagon bases, but still rectangles for the sides that connect those. And so the idea here, okay, is the area of the base multiplied by the height still the same full correct volume as it was when we had a rectangular base? And the answer, I believe you should have arrived at, is that yes it is. So for example, when we look at this triangular prism, and I'll pull up just a quick place to write, we had a triangular prism that had bases. Ooh. Let's try that one more time with a straight edge on the screen to really get a nice right triangle. So bases that were 3, 4, 5 right triangles. And you'll notice, again, with a look back at the lesson, even though the 5's not given, it's a right triangle with 3 and 4, so we can use that shortcut. So we've got that base, meaning we have an area that's 1/2 times 3 times 4, which ends up being 3 times 2, or 6 square units. And since we have that area of 6 square units, we can then multiply it by the 9 unit height to get a total of 54 cubic units. And that is the correct volume for that figure. So it turns out that process we came up with for finding the area of a base and then multiplying by the height can work regardless of the shape of the base. Same would be true for the hexagonal prism as well. Surface area, nothing changes there. You have a greater number of surfaces on some than others, but those surfaces, or the lateral faces, they should all have a similar or congruent set of side lengths on them, so you can simply find the area of one of them and multiply it by the number. When we moved into the cylinder, things looked seemingly pretty different. I see that we have circular bases, but then I don't see those nice rectangular lateral faces of this figure like we had with the prisms. So at first it might be a little hard to visualize. However, if you really think about what would happen to create that connector between your two circle bases, you might find a familiar shape. So if we go back and take a look, let's clear what we've got here, and we break down the cylinder a little bit, we could look at it as a circle on top, and then this is essentially a net. We could connect the top base, which was just drawn, if I can get my straight edge, to the lower base, oh boy, which I'm drawing now, as you guys patiently let me draw. But we can connect that circular base with a matching circular base. Got to be a better circle than that. That would be rolled along this rectangular edge if we were to fold this up into a net. So you have these circles that are in fact connected together by one rectangle rolled upon itself. And that's really powerful, because then when we think about this rectangle, we've got a whole lot of information that we can use to make sense out of what it means to find the surface area and even the volume of this cylinder. So in the example, our cylinder had a radius of 5 units and a height of 8. So we were 5 units on the circle, the height was 8, and that was all the information they gave us. Well, fortunately, there's a lot of information in those circles, so if we just want the area of the circle, we know that the area of one circle is going to be equal to pi times the radius squared, or 25 pi. So that's for each circle. And we'll just call that units squared, units squared. And with that, we can actually find the volume right away. The volume is going to be equal to the area of one base, so 25 pi units squared, multiplied by the height, which was 8 units. When we do 25 times 8, that gives us 200. We still have pi along with it, and now that's in units cubed. So we've got the volume without all that much work. For the surface area, well, right away we can add our two circular bases areas, so 25 pi units squared plus 25 pi units squared, and then we need to continue to add the area of that rectangle. Good news, the area of the rectangle is still equal to the base times the height, or the length times the width. We just need to take an extra step to figure out that missing dimension. We know 8 is there as the height, so it's going to be 8 multiplied by, well, if that rectangle rolls along the entire edge of that circle, it should match that circle's circumference. So it's a good thing we know the equation for a circle's circumference, which is the diameter of the circle multiplied by pi, or 2 times pi times the radius. Let's do the latter since we were given the radius. So 2 multiplied by pi multiplied by 5, and just for consistency we'll keep those as units. And now we can simply simplify this equation, and we'll get 50 pi units squared plus 8 units multiplied by 10 pi units, and then finally simplifying that all the way out, we get 130 pi units squared. So that takes a little bit more work to find the surface area, but it relies on our knowledge of a circle to get our way into some information on that rectangle and find its overall area. And that's a process we can use on any cylinder. All right, last main idea that showed up here was related to Cavalieri's principle, talking about oblique cylinders or prisms, which are those that are slanted and have a height that does not fall directly along one of the sides of that figure. And that's exactly what's pictured in 9-31. And so they gave some great visuals thinking about piling pennies and then pushing it at a slant, or using textbooks, or think about notebook paper or printer paper, say if you were to slant it. And there's a good way that you can really see, no, the overall volume does not change as we make that into an oblique, so we can still use that same method for calculating the volume as we did traditionally. Those were the key ideas from this lesson. Please make sure you're keeping very neat and organized notes and work from the problems you're doing here. And then part of this assignment as well is to go on and do the review and preview. That is what you're going to take a picture of and submit on Google Classroom as a finished assignment. Just a reminder, I have office hours from 9 to 11 on the weekdays, so please put your questions into Google Classroom and I'll be answering those promptly. And good luck. Let me know if you have